Hello everyone and welcome to Robot Operating System version 2 or ROS2 Jazzy Jalisco tutorials. In this tutorial we explain number 1, the basics of ROS2 joint state and robot state publishers and how they fit into the big picture of controlling robot models. Then we explain how to create a minimal unified robot description format or URDF file format and model for modeling the geometry of a robot. Then we explain how to create a ROS2 Jazzy package and launch file for visualizing the URDF model that you can see over here. And we explain how to visualize and control the robot motion in RViz and ROS2 Jazzy Jalisco. This robot model over here consists of 3 links, the first link, the second link, and the third link. And it consists of 2 joints that can be independently controlled. This model is deliberately chosen to be as simple as possible in order not to blur the main ideas of creating URDF file and launch files with too many modeling details. However, this model is still relatively complex since behind the scenes you have several ROS2 nodes and topics that are running concurrently and in parallel. Everything explained in this video tutorial can be straightforwardly generalized to more complex robot geometries and to robots with full 6 degrees or even more degrees of freedom. In this video tutorial, you will learn how to write a ROS2 Jazzy Jalisco package from scratch and in addition this URDF file that defines the robot geometry and possible motions. Then you will learn how to write this launch file. This launch file is used to run several ROS2 nodes at the same time and it enables us to visualize and to control the motion of robot in RViz by using this small and simple graphics user interface. In addition to this package and to these files, we have created a detailed manual explaining all the steps that we need to perform in order to visualize the robot in RViz and in order to control it. And here is the manual. The manual contains more than 10 pages and it explains all the steps. You even have in this manual this nice graph showing the robot geometry and showing how the coordinate systems are placed. Links to this manual as well as to all the files including package, launch, Python, URDF files will be given in the description below this video tutorial. Before we start with explanations, it's very important to mention the following. First of all, this video tutorial is created for people who know very little about ROS2, Linux, and robotics, and consequently, we will spend a significant amount of time explaining the basic concepts. Okay, let's start with explanations. But first, let's again briefly summarize what is explained in this video tutorial and let's clearly explain the used terms. First of all, in this video tutorial, we explained the basics of ROS2 joint state and robot state publishers and how they fit into the big picture of controlling robot models. Then, we explained how to create a minimal unified robot description format or URDF file format and model for modeling the geometry of a robot. Then we explain how to create a ROS2 Jazzy package and launch files for visualizing the URDF model, and we finally explain how to visualize and control the robot motion in RViz and ROS2 Jazzy Jalisco. Okay, let's now explain the basic terms since a lot of viewers of this video are completely new to ROS2. First of all, what is a URDF file format? URDF file format is a widely used XML file format for describing the geometry and configuration of robots. It's used in ROS and Gazebo to define the geometry, joints, and configuration of robots. Okay, now what is RViz? RViz is a 3D visualization tool and more than that for ROS2. What are the launch files? Launch files are ROS2 files that are used to configure and run at the same time a number of ROS2 nodes and other components of a ROS2 system. For example, with a single launch file, which is often written in Python, although you can use other programming languages, you can run a number of different nodes and components for controlling a mobile robot. That is, with a single file, you can run several nodes or several components of a ROS2 system at the same time. Here's the license and copyright notice. This document, developed code files, lesson video, and all the provided material are referred to as the learning material in the sequel. Number 1. The learning material is the ownership and the original work of Dr. Alexander Haber, who is referred to as the author in the sequel. Number 2. You have the right to use the learning material for personal educational use and strictly for non-commercial use. Number 3. The learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. Number 4. The learning material should not be reproduced manually or automatically, for example, by using an AI algorithm or an AI model from this video and then posted on public or private online repositories. Number 5. Unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in university courses. Number 6. Unless allowed by the author, the learning material should not be used to train engineers working in companies or paid academic research, such as paid students, paid postdocs, and paid professors. Number 7. The provided code files in the learning material should not be used to train an AI algorithm or a large language model. And number 8. Unless allowed by the author, the learning material should not be used to produce academic papers, student reports, or other documents. Let's start with the prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows subsystem for Linux or WSL since you might have issues displaying the graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. So let's verify that you have the correct Linux Ubuntu version. Over here, I'm going to resize this window and I'm going to start a terminal. Okay, to start a terminal, simply click here and search for terminal. Once the terminal is open, let's verify that we have the correct Linux Ubuntu distribution. To do that, you simply need to type this command. And as the result, you should see this. 24.04. This last number is really not important. The most important number are these two numbers. Okay. Next, you need to verify that you have ROS2 Jazzy Jalisco installed on your system. To verify that ROS2 Jazzy installed, open a terminal and in the terminal you need to type this. This command will list the content of the standard installation folder for ROS2 Jazzy, and if you see something like this, this is the first good sign. Then, let us thoroughly verify that ROS2 Jazzy Jalisco is installed. To do that, we simply need to execute this command, which will run the setup.bash script of ROS2 Jazzy. And if you don't see any error, that's a good sign. Very good. And as the final check, let's print this environment variable, and as the result, you should obtain Jazzy. If all these three steps do not produce any error, this means that ROS2 Jazzy Jalisco is properly installed on your system and we can continue further. If for some reason ROS2 Jazzy Jalisco is not installed on your system, then on my YouTube channel you have a number of tutorials explaining how to properly install and configure ROS2 Jazzy Jalisco on a Linux Ubuntu system. Good. Let's explain the basic terms. First, let's focus on this graph. This graph is called the RQT graph and it shows the basic structure of the ROS2 communication system. Over here we have three nodes. Here's the first node, here's the second node, and here's the third node. The links are actually the topics that are used to communicate information. Over here we have one link, we have second link, and we have third link. Let's first focus on this node called Joint State Publisher Graphics User Interface. This node brings up this graphics user interface for setting the joint 1 and joint 2 position and rotation. Namely, if I go back to my RViz simulation, by using this slider I can rotate the first joint, and by using this slider I can move or translate the second prismatic joint. This node helps the user to set the position and angle of rotation, and then it publishes something. And that something is actually the joint state. That is, for every joint we have a state. You can think of as this node also serving as a sensor. Namely, in every joint on the robot system we might have an encoder, either an angular or rotary encoder, or you might have a linear encoder measuring the position or the angle of rotation, and you can think of as this node providing this information. However, the joint state is more than that, and we will clearly define the joint state in the sequel and what is being transmitted through joint state topic. Then, the information about the joint states is transmitted to the robot state publisher. Robot state publisher is maybe one of the most fundamental nodes in the ROS2 system. This node receives joint state information, then on the basis of the URDF model, that is on the basis of the geometry of the robot and the configuration of all the joints, it publishes some information through this topic called TF. And it uses the forward kinematics to calculate the mutual orientation and pose of the complete robot. Then this information is sent through this TF topic. It will be explained in the sequel. And over here we have transform listener node, which help our RViz node to actually display the position and orientation of every joint. And again, if we use this slider, we are actually able to move everything. However, behind the scene, this is happening. To be able to properly implement a control algorithm for ROS2, it's very important to properly understand the state of each joint. Consequently, let's clearly define what is the state of every joint. In ROS2, the state of each joint, either revolute or prismatic, is defined by number 1, the position or the angle of rotation of the joint. In the case of revolute joints, the component of the state is the angle of rotation, expressed in radians or briefly rad. In the case of prismatic joints, the state is the position of the joint, expressed in meters or briefly m. Number 2, the linear or angular velocity of the joint. In the case of revolute joints, the components of the state is the angular velocity in radians per second or briefly rad per seconds. In the case of prismatic joints, the component of the state is the linear velocity, expressed in meters per second or briefly ms. Then, the third component of the state is the force or torque, both referred to as the effort in the ROS2 documentation. And the force or the torque are the force or the torques that are applied to every joint. In the case of the revolute joint, the component of the state is the applied torque, expressed in Newton meters or briefly Nm. In the case of prismatic joints, the component of the state is the applied force to the joint, expressed in newtons or briefly N. Note that this definition of the state is different from the kinematic definition of the state, which only takes into account the position or angle of rotation and velocity or angular velocity. For example, if you studied control engineering, or if you take a single control engineering class, then you might be familiar with the state space model. In the state space models, the states are actually kinematic states and forces or torques are inputs. In the case of ROS2, the situation is slightly different, since also the force or torques are considered as a component of the state of every joint. The state is communicated or published or received by using the topic called joint states. You can obtain the information about this topic by typing this command. Of course, after everything is being built. And let me show you that. So what I will do here, I'm going to go back to the terminal, and then over here I'm going to type this command, and oops, over here it's not being sourced. So let me do this. And let me show you what's happening. Now over here you will obtain this information. You will obtain sensor message joint state. This is the type of the message being sent through this topic, and you can see the publisher count and you can see the subscriber count to this joint state topic. Don't worry about this. If you cannot run this at this point, you will be able to verify this at the end of this video tutorial. Next, let's explain what robot state publisher node is actually doing. The state information is received by the node called robot state publisher. As you can see it from the RQT graph over here, joint state topic, joint state information received by robot state publisher. This node receives the state information for every join, and by using the URDF model of the robot, publishes 3D poses of the robot links using a kinematic tree of the robot. The node robot state publisher makes use of the URDF robot description defined by the parameter robot description and the joint position from the topic joint states to calculate the forward kinematics of the robot and publish the results to the TF2 topic. That is, the state of the robot is published to the TF2. And let's see that. So here is TF. TF is actually TF2, so don't be confused. TF2 is a transform library that is used to keep track of the relationship between coordinate frames over time. It maintains a tree structure describing the relationship between the coordinate frames. Also, this library enables us to transform vectors, points, or any quantity between any two coordinate frames. So to summarize, Robot State Publisher publishes 3D poses to the TF, and then this information is passed down the chain to transform listener node. So where is this node? Here it is. And then the RViz node, which is another node in the ROS communication graph and not shown on this graph, is actually updating graphically the position and orientation of the complete robot. And finally, once we have defined everything, let's start with building. The first step is to install the necessary ROS2 packages and to verify that they are installed. As explained previously, we will need several nodes, and in that sense, we will need to install ROS2 Jazzy Joint State Publisher GUI for the Joint State Publisher GUI. Then we need to install ROS2 Jazzy Robot State Publisher for the Robot State Publisher node, and then we will need to install ROS2 Jazzy RViz package. Most likely you have these packages if you use the standard way of installing ROS. However, let's still try to install them since it will not hurt. So let's start here and search for terminal and then open the terminal. And remember, whenever you want to play with ROS or to do something, make sure that you source the ROS environment. You can do it like this. Then let's install the GUI Joint State Publisher. Enter your password. As you can see over here, it's already installed on my system. Then let's install the Robot State Publisher. It's already been installed, and let's install the RViz by running this, and RViz is installed. To list all the packages on your ROS system, you need to run this command, and you can see all the packages. This is beautiful. However, since there might be hundreds of packages and you want to search for a particular package, you can search easily and find the package you're interested in by using the grep. So what we are typing here is ROS2 package list, and then here we are filtering, we are using grep, and then we want to find joint in the name of any package, and if you type this, you will see all the packages contain joint in their names. You can see joint state publisher and joint state publisher GUI. This is the package I'm interested. Then let's repeat this for state to find the robot state publisher. Here's the robot state publisher. And then finally, let's do this for RViz to make sure that RViz is on our system. And you can see RViz2. This is the package that we will use inside in this video tutorial. The next step is to create the package folder, to create the URDF files and the launch files. So let's practice this procedure again. Let's close this terminal and let's practice sourcing. Let's open a new terminal, and inside of this terminal, let's start from scratch by sourcing the base ROS environment, that is by creating an underlay. We do that by executing setup.bash configuration file. Then let's navigate to our home folder, and inside of the home folder, let's create two folders, one inside another one. The first folder is demo_ws. This is our base workspace folder, and inside of that folder, we are going to create the folder src, short for source, which will be used to store the package source files. Good. And the next step is to create our first package, or to create an empty package. Here you have two options for creating a package. The first option is to use a C++ build system, and the second approach is to use the Python build system. Here we are going to use the C++ build system. However, we are not going to write any C++ code in this video tutorial. We'll just create the source file structure by using the C++ package builder. So let's navigate to the source folder. Remember, whenever you want to create a package, you need to be in the source folder. Inside of that source folder, we need to create an empty package. And to do that, we need to run this command. Let's first explain what this command is doing before executing it. We are calling ROS2, then package create. This command is used to say, okay, I want to create a package. Then over here, you need to specify the build type. We are going to use ament CMake. CMake is the standard C++ CMake approach for writing configuration files and for compiling. And finally, you need to specify the package name. In my case, it's demo_robot. However, you can also use some other package name. But if you use some other package name, remember to change this package name in all the files. If you're completely new to ROS2, don't change the package name, use my package name and press enter. And let's see what happened. Now inside of this source folder, you have another folder. It's called demo_robot, and that's precisely the name of your package. The idea over here is that in the source folder, you can have several packages, and consequently, you will have a single folder for every package. So let's navigate to this package folder and let's see what is inside. We have several important things. We have CMake lists.txt file. This is the CMake compilation file that's used to define how your package is being compiled, that is how it's being built. Then you have include for including some header files or something similar. Then you have package.xml. This is another configuration file that we will also have to edit later on. And inside you have the source folder. The source folder is the folder that will be used to store the source files. Inside of this package folder, we need to create 3 additional folders. And to do that, let's execute this command. This command will create a folder called launch, then it will create a folder called URDF, and it will create a folder called config. So let's now list these folders. Here they are, and let's explain what they are. First of all, the config folder will contain the RViz configuration file. We are going to create this file at the end. Then we have the launch folder, and this folder will create, or actually will hold, the launch file that's used to run all the nodes. And then finally we have the URDF folder, and this folder will be used to store the URDF model file. And it's very important that you stick to this convention for creating URDF files or creating this folder structure. Okay, the next step is to write a URDF file. For that purpose, we're going to use this two-dimensional sketch of our robot. In ROS2 world and in ROS2 terminology, robots are composed of links and joints. So let's explain what are links. Links are parts of the robot. Namely, our robot consists of 3 links. This is the first link, the second one, and the third link. And keep in mind that this is actually a two-dimensional projection. First of all, we have the base. In three-dimensional space, the base is a cylinder, and consequently, this will be our base link, which is a cylinder. Then, we have the second link, which again is a cylinder, and we will call it as first underscore link. Then we have the third link, which is a prismatic link, shown over here. Between links, we have joints. So joints are used to connect links, and joints enable relative motion with one link with respect to another link. Between the first and the second link, that is between the base link and the first link, we have the joint over here, and this is joint 1. Then between first link and the second link, which is actually a box, we have another joint, and we call this joint 2. Joint 1 enables the first link, that is the cylinder, to rotate with respect to base, and joint 2 enables the second link to translate with respect to the first link. That is, the second link can translate in this direction, then first link can rotate with respect to the base link. In order to properly define the robot geometry and relative motion between different links of the robot, we need to associate different coordinate systems with joints and links. Over here you can see C1, C2, C3, C4, and C5, which are coordinate systems or coordinate frames associated with links and joints. Let's start with C1. C1 is the fixed coordinate system that is inertial. That is, C1 doesn't move. Then we have C2, which is a coordinate system associated with joint 1. And we can see the displacement between C1 and C2 over here. Then C3 is the coordinate system or coordinate frame centered at the center of the first link. Then we have the coordinate system or coordinate frame C4, which is associated with joint 2, and it's displaced for 0.5 with respect to the joint 1 coordinate system C2. Then we have the coordinate system C5, which is centered at the center of the second link, and this frame is displaced for 0.05 with respect to C4. The next step is to write the URDF file that implements this robot geometry. To do that, let's navigate to the URDF folder, and inside of this folder, let's start Visual Studio Code. If you don't have a Visual Studio Code installed on your system, then you can use some other editor, or you can also install Visual Studio Code by following one of my tutorials, whose link will be posted in the description below. Okay. So let's create a new file, called File, New File, and over here it's very important to give the proper name to this file. The name of the file should be model.urdf. So let's write it down here. Let me do it again. File, New File, and let's call it as model.urdf. Here it is. Let's save it inside of the URDF folder. This is very important. And over here, to save time, I'm going to simply paste the content of this file, and I'm going to explain this file line by line. To do that, I'm going to minimize this screen over here, such that at the same time we can look at the graph, and we can analyze the code and explain what is written inside of this code. Okay, so I'm going to minimize this like this. This goes like here. Let me do this, and let's start. Okay, so every URDF file is actually an XML file, and consequently you need to write this line. Then let's learn how to write comments. We write comments like this. You start comments this way, you end them in this way, and actually this line is not necessary. This line will just point to the link that explains URDF XML files. And here's the first line that really matters. This is basically the line defining the robot name. I will call the robot as simple underscore robot. And then the next step is to define the first link. So what is the first link? Here is the first link, this cylinder over here. How to define the link? Well, to define the link, we need to do several things. We need to start the link environment and we need to close the link environment. Everything in between defines the link. Okay, first of all, we need to specify the link geometry. So let's see our link. Our link is actually cylinder. So we need to type geometry, close the geometry environment. Then we need to specify cylinder. But before we do that, yes, I forgot to say this. Inside of the link, you need to start the visual and you need to end the visual. This means that you are defining a visual representation of the link. This is very, very important. So then inside of visual, we have geometry and we are closing the geometry definition. We are specifying the cylinder length. Let's see. This is actually the height of the cylinder. It's 0.1. And note over here that all the dimensions are meters, and we need to specify the radius. The radius is 0.3, which brings the diameter to 0.6. Next, we need to define the origin, and this is very, very important. So here comes the origin. So how do we define an origin? What is the origin? For this particular link, the origin is placed actually at the C1, and C1 is a fixed coordinate frame of the fixed joint. That is the joint that is completely attached to the ground and doesn't move. This is a fictitious joint that's used to simulate the robot and to have the absolute reference. And over here, we need to define the location of the coordinate system attached to the center of our link with respect to that fictitious or fixed coordinate system. And we have several parameters that we need to define. When we define one frame with respect to another frame, we need to define the rotation of the second frame with respect to the first frame, and we need to define the displacement. So over here, RPY, R is the roll, pitch and yaw, these are the basic rotation angles. They are all 0, 0, 0, and they should be specified in radians if the values are non-zero. And over here we specify displacement 0, 0, 0. This means that we are actually placing the center of this first link inside of C1. And then over here you need to specify material. This is actually not blue, this is other color I think, but never mind. So, and then you need to specify the color, let me correct this. You need to specify the color code RGBA, and here it is, and that's it. And you end visual, you end link, and you are done with the first link. Good so far. The next step is to define the first joint. So here is our first joint. The first joint connects the base link and the first link. So let's start with the definition. We have joint name is joint 1. Type is revolute. Revolute means that the joint can rotate. In fact, the joint is not rotating. What is rotating is that this link, first link, is actually rotating with respect to base link. However, we are still saying that the joint is rotating. Then we need to specify the parent link and the child link. Namely, the kinematic chain in ROS2 and URDF is defined by using parent-child relationship. The parent link is obviously the base link, that's why we write it like this, and the child link is actually the first link shown over here. Good. Then we need to specify the origin or the center of the coordinate system that's attached with the first joint or joint 1. Now here comes a very important thing. The position and orientation of the coordinate system attached with joint 1 is defined with respect to the fixed joint, that is to the joint whose coordinate system is C1. And this is very important to keep in mind. When you define a coordinate system of one joint, that definition is always given with respect to the coordinate system of the previous joint. And over here, let's see what happens. We have only the displacement in the z direction. Consequently, we have 0.05 over here. We don't have the rotation. And over here comes a very important part. We need to specify the axis of rotation. Let's see over here. This cylinder is rotating around the z-axis with respect to the base, and consequently the axis of rotation is 0, 0, 1. Then we need to specify the limit effort, which is basically the torque limit. We need to specify the velocity and lower and upper limits. You can change these lower and upper limits as you wish, as well as the velocity and the effort. And all these values are given actually in radians. And that's the first joint. Simple as that. Next, let's proceed with the first link. So here's our first link. So let's start with the definition. Again, link name is first link. Good. Visual representation and visual representation. Also, and the link with the proper mark over here. Then we start geometry definition. Again, it's a cylinder. What is the length of this cylinder? It is 0.5. What is the radius of this cylinder? Well, let's see that. Is the radius given over here? Yes, it is. 0.08. Good. And now we need to specify the origin. If you put 0, 0, 0, 0, 0, 0, the center of this link C3 will be actually placed at the center of the joint 1. And this is what we don't want. We want to displace C3, and the displacement is 0, 0, 0, 0.25 in the z direction, and we don't have any rotation of coordinate systems. We specify the color. Here it is. We end the material, we end the visual, we end the link, and that's it. Simple as that. Next, we proceed with the joint 2. Here is how we define joint 2. Start definition and definition. And then we need to say what is the parent link. Well, the parent link, let's see, obviously is the first link, and the child link is the second link. Interesting. So now we need to define the origin of the second joint. So where is the origin? Well, the origin definition should be defined with respect to the origin, or better to say with respect to the previous joint. The previous joint is joint 1. And if we now look into this picture over here, we can see that joint 2 coordinate system is displaced with respect to joint 1 coordinate system only for 0.5 in the z direction. And that's precisely what is written over here. We don't have rotations of the coordinate axis. And over here we need to specify a very important thing. We need to specify the translation direction. Note over here that when defining joint 2, we specify the type to be prismatic. This means that this joint will actually translate. Okay, so let's see what is the translation axis. It's the y-axis, and the y-axis is this axis over here. This is very, very important. Then we need to specify the force, 300 newtons. We need to specify velocity and lower and upper limits. You can change these lower and upper limits as well as the velocity. Okay, so this was the definition of joint. Next, we need to define our final link, which is a second link. Here it is. Here is the visual representation. Its geometry is defined like this. It's a box. We need to define the size. Width in the x direction, height in the y direction, and extension in the z direction. Then we need to specify the origin. Its origin is defined with respect to the origin of join 2, and it's being displaced only for 0.05 in the z direction. Then we need to specify the material. The material is over here, red. Again, this might be confusing over here since this might be blue in the picture. But anyway, so I should put here blue to be more precise. Okay, let me save this, and that's it. Simple as that. We end the link and we end the robot environment. So let me show you again the file. So here it is until line 29. And after line 29, it looks like this until the line 55. And here's the end. Good. Next, make sure that you save this file by pressing Ctrl S, and then let's go back to terminal and let's type this, and here's the file, and here's one error I created. The file name should be model, not mode. So let's correct this. Let me now go here and let me correct this. So let me just go to home. Let me go to demo, here, URDF file, and let me rename the file. But let me just close this one such that it doesn't create an issue, and it's very important to keep it as model. Okay, this is very, very important. Good. Let's continue. So let's go back here and let's verify the file name. Yes, it's model.urdf. Good. The next step is to create the launch file. To create the launch file, we need to navigate to the launch folder. And over here again, I'm going to start Visual Studio Code. And it's very important to give the proper name to this file. The name of the file should match a very standard name. Let me now just bring up the name. The file name should be display.launch.py. Okay, so keep in mind that. So let's go here and let's click on File, New File, and let's call it display.launch.py. Here it is. Make sure that you save this file. And over here, to save time, I'm simply going to copy and paste the content of the file. And let's explain what this file is doing first. This file will bring up several nodes. It will bring up the GUI node for setting the robot state. It will bring up the robot state publisher, and it will bring up the RViz. It will also define several parameters. First of all, you need to import launch. You need to import launch.substitution, command, and launch configuration. Then you need to import launch ROS, and then you need to import OS. Here we need to define the package name. The package name is demo_robot, and over here we need to define the relative file path, that is the URDF relative file path with respect to the package path. Here it is. So what is this path? This path is actually the path with respect to this folder. Okay, so the path with respect to this folder of the URDF file is URDF, then model.urdf. Then we need to specify another relative path. We need to specify the relative path for the RViz configuration file. Note over here that the RViz configuration file is still not being created. However, although it's not being created, we can still give it a path and a name. The file name will be config.rviz, and this file will be created at the end. Okay. So here's the function that brings up all the nodes. Usually we call this function generate_launch description. And let's see what this file is actually doing. First of all, we need to define the absolute model path. That is the absolute path of our URDF file. We need to bring up or retrieve the package path. To do that, we use launch_ROS, which is a function we just imported. Then we need to use substitution. Then we need to use this function find package share. We specify the package name. Note that the package name is defined over here, and we want to find the package name. This will bring up the absolute path of our package folder. Then what do? We just need to glue the absolute path with the relative path to get the complete path of the URDF file. Although this might look complex, that is, we are playing here with different paths, we can simply say here URDF model path and then just retrieve the URDF model path to our file. We can simply do it like this and have a hard-coded path. However, this is still not a good practice, and there is a good reason for that. It will be explained in the future video tutorials. Okay, the same thing needs to be done with the RViz configuration file. Once we have the package path, we just add the RViz relative path, and we got the RViz configuration path file absolute path. Okay, over here I'm printing the path for verification. That is the path to the URDF model. And here comes a very important thing. Over here, we load the robot description. That is, we are actually opening the URDF file specified by this path. We are saying that we want to read the content of the file. And over here, we are actually reading the content of the file and storing everything inside of this string robot underscore desk, which is actually robot description. And we are using with since we want to make sure once this segment is completed, the file will be automatically closed. Here comes another very important thing. To pass the URDF file to certain nodes, such as the joint state publisher and robot state publisher, we need to define this dictionary called params. And over here we need to specify the key robot underscore description, where we pass the complete description, that is the complete URDF file. Okay, then we need to create the robot state publisher node. It's relatively simple. We call launch ROS.action node. We specify the name of the package, it's robot state publisher. We specify the name of the executable. Usually the name of the executable matches the package name, where we want to print out screen, and then we are passing over here the URDF file like this, and then we additionally pass also the URDF model path as a complete string, and that's it. This will actually launch the robot state publisher node. Now, over here, note that I commented the joint state publisher node. Why I did that? Well, besides joint state publisher node graphics user interface, which we are using in this video tutorial, you also have joint state publisher node package. These are two different packages. The package we are using is package for graphics user interface definition. However, the package joint state publisher node is a package that does not contain a graphics user interface, and you will have to manually set the states of the node. If you want to include this package, you can, or actually this node, you can do it like this. However, if you uncomment this part over here, and if you keep the joint state publisher node graphics user interface on, that is, if you use both of these 20 lines or whatever they are, you will have an issue. That is, the position of the robot will not be updated. And I discovered that that might be a bug or something that is going wrong with ROS2 Jazzy. In ROS2 Humble, this was not an issue. That is, at the same time, you can run the node joint state publisher and the node joint state publisher graphics user interface. Consequently, I commented this part over here. Okay, and here's our joint state publisher node graphics user interface. The principle is the same. You define the package, you define the executable, then you define the name, and then you specify the arguments. The arguments are just the URDF model path. And then over here, I'm having this condition, launch configuration GUI. You can actually turn it on or turn it off. Here it will be turned on. And finally, I have the RViz node. Let me now explain one additional thing. Here I'm declaring the launch argument, and it will be true. And the graphics user interface of joint state publisher will be automatically started. this will be explained in a second. Here is our RViz node. How to run the RViz node? The principle is the same. Package, executable, name. Where we want to output it, we want to output it on the screen. And then over here, I'm specifying RViz configuration path. That is, this is the path to the RViz configuration file. Note over here that the first time we are executing RViz node, the configuration file will not exist. Consequently, this will be completely empty since the file doesn't exist. However, the first time we run RViz, we are going to configure RViz and we are going to save the configuration file, and the name will be config.rviz, and the next time we start RViz, that configuration file will be loaded. Okay. And finally, we combine everything and return. We simply return launch.description, and then you have this list defining everything. Over here, I have a launch argument, which will be used to start the graphics user interface for joint state publisher GUI. And then over here, what I'm starting robot state publisher node, I'm starting joint state publisher GUI node, and I'm starting RViz node. Note over here that I commented this part since, as explained previously, joint state publisher and joint state publisher GUI node do not work together for some reason in ROS2 Jazzy Jalisco. Next, make sure that you save this file. Okay, and now we have everything. The next step is to modify configuration files. Namely, if you go back to the Workspace folder of our package, you'll see these two files, cmakelist.txt and package.xml. We need to modify both of these files. So let's start with the package.xml. Let's open it from the Visual Studio Code. Let's go to the package folder. Here it is. Open it up. And over here, we'll have to do several modifications. Here, we need to set the dependencies. That is, we need to say to our ROS2 system that the created package actually depends on these three packages: joint state publisher GUI, robot state publisher, and RViz. That is, these are the packages that we are running, or better to say, we are running nodes from these packages. So let's save this file, and that's it. Next, we need to change, or we need to modify the configuration cmake file. So let's open that file again. Here it is. Open the file, and here it is. Over here, we need to tell to cmake build system that we have 3 additional folders and we have files inside. So how to do that? Well, simple. If you're familiar with cmake, these steps are straightforward. However, for people who are completely new to ROS or C++ compiling, this might look terrible. However, it's not. It's relatively simple. Here you're using this command, install, and what are you installing? You're installing directory or telling to the cmake system where to look for files, and here you're specifying destination. This will be the final destination after everything is compiled. So what are the folders? Well, if you go back to terminals, the folders we created are config, launch, and URDF, and you need to specify them over here. Then you need to save, and that should be it. Make sure that you also save the package.xml file. The final step is to build the project. So how to do that? Well, to build a project, let's go back to the base folder. Here it is. Okay, and inside of this folder, we need to run the build command. You have to be in the same terminal in which you executed the source command that executed the configuration file setup.bash. This is very important, otherwise the build command will not run. However, before we actually build everything, let's make sure that ROS2 dependencies are properly installed. To install ROS2, let's run this command. enter your password. Then let's initialize ROS2. You can simply ignore the error over here if the error occurs. And let's update the ROS2. And then finally, let's run this command to verify that all the dependencies on our system are properly installed. And you should get something like this. All required ROS2 dependencies installed successfully. Good. And finally, we can build our package. To do that, you need to execute this command. Let's explain what this command actually doing. Okay, so we're calling colcon build, which is similar to cmake. Then we are telling this option simulink install, and then we need to select a particular package, and we are selecting demo_robot. This is the package we just created. Instead of all these things, you can simply try colcon build and without any parameters, and this will build all the packages. And since we have one package, this will work. However, imagine that you have hundreds of packages, and if you run colcon build on everything, then everything will be built. So it's better to run it like this. That is to explicitly specify the package. And let's press enter, and let's hope that there will be no errors. No errors. Perfect. The final step is to run everything. So how to run everything? Well, open a new terminal. In this terminal, you need to source only the package folder. You can go to any folder, or no, better to say I made an error here. Not to source the package folder, you need to source the setup.bash file from your package. So execute this, and here you created an overlay. Remember, when you want to execute the created nodes from the created packages, you don't need to source the underlay. You just need to source the setup.bash file. Okay, and then let's run our launch file. We are calling ROS2 launch, then the name of the package and the name of the file, and bang. And let's see what happens. Don't skip this part, and let's see what's happening over here. Always read the log. Okay. Here I printed out the absolute path from my launch file, and you can see the line over here. Here it is. This is very good for debugging, right? You can actually print everything. Then over here, let's see what's written. Robot state publisher started successfully. Robot state publisher GUI started successfully. Perfect. RViz node started successfully. So all three nodes are started with no issues. Then let's see what's happening. Robot initialized. So no errors. That is, always hunt here for errors. So let's see our RViz. Wow, nothing, right? So is there some error over here? Well, there is no error. Why is that? We didn't create an RViz configuration file. That is, we didn't tell to RViz how to load everything. So let's fix that issue. First of all, over here, click on add, then go down and search for robot model. Click on OK. Then expand over here. And over here, make sure the topic is selected and description topic is actually set to robot description. And if you click here, something happened. That is, you can see the links over here. However, the links are not ordered correctly. So why is that? Because the fixed frame is not properly being selected. Click on here and click on base link. And now you can see the fixed frame is properly set, and here's your robot. And that's about it. Now we have properly set up the RViz, and we can see our robot configuration. However, let's try to move the robot. Now if you focus over here, you will see the GUI of joint state publisher, and if you start moving, you will see beautiful thing. You can see the first joint is moving and the second joint is also moving, and you can see it over here. Of course, this joint limits are not realistic since this joint can go all the way there. However, this is not a big issue. The next very important step is to save this file such that the next time we run RViz, this configuration will be automatically loaded. So let's learn how to do that. Well, this is relatively simple. So the file name should be config.rviz, and if you go over here, here's the file and here's the path to this file. So let's save this file. To save this file, let's just copy this name, then go back to RViz, click on File, Save Config As, and then here you need to find the proper path. Go back to the base workspace folder, go to Source, go to the demo robot, then go to the config and save it over here. Call the file as, oops, I made an error, config.rviz, save, again, the name should match this name. Now, let's now close everything. Let me just go here, close RViz. Let's go back to terminal. I'm going to press Ctrl C, and then over here we need to rebuild this package. So again, run this to rebuild the package. After you rebuild the package, go back to this screen, and then again you need to source back the setup.bash file since we rebuild everything, and if you run this again, beautiful thing will happen. Your robot will be automatically loaded with all the configuration. Good. As the final exercise in this video tutorial, let's learn how to visualize the ROS2 communication graph. First of all, open a new terminal and run these two commands in order to update and upgrade everything. Then enter your password, and let's install ROS2 Jazzy RQT graph tool. To do that, you simply need to execute this command. And after that, let's source the environment. And finally, let's start the RQT graph. We start it like this. Okay, and here it is. So here's our join state publisher, join state, robot state publisher, TFs, and transform listener. Next, let's learn how to obtain more information about the topics, nodes, etc. For that purpose, open a new terminal. Again, you need to source the environment. To source the environment, you need to execute a very famous source command, that is this one. And let's see all the nodes. To do that, type ROS node list. And let's see what's happening. Join state publisher, robot state publisher, RQT graphics user interface, RViz2, and transform listener. Perfect. So let's see all the topics. To do that, simply type here topic list, and you'll see all the topics. You can see join states, you can see TFs, you can see robot description, and other important topics. You can obtain more information about certain topics. For example, let's see what is being communicated through join state topic, and you can see the type of message, sensor message, join state, and let's obtain more information about this message. We can simply type this, and you can see what is being transferred through this message. You can see that these are the joined states. Okay, that's all for today. I